Okay guys, so let's go ahead and talk about hidden Markov models. So far we know about Markov chains, and we also know about dynamic programming. So this is the best time that we should go and learn these hidden Markov models. A statistical Markov model in which the system being modeled is assumed to be a Markov process with unobserved or hidden states. So that's what we call it as hidden Markov model, represented as M. And it has following components: Q, which is the set of states, and sigma represents symbols, A represents the transition probabilities, and E represents the emission probabilities. So these four components, they are the important components of hidden Markov model. So as I said, Q is set of states. So you can have one through many stages, many states. So for example, you can have coding genes versus non-coding gene models. So in that case, you have two states, head and tail, again two states, a fair and loaded die. These are again two states. And sometimes you have more than two or up to n number of states. Alphabet is the, in case of the DNA, we see we can take DNA also as a like a die, like your normal die, which is 6-sided. So we can say DNA can be a 4-sided die, where your alphabet can be ATGCs. In regular die, you have 1 through 6. So here, in case of the DNA, you can also treat it as a die where you have 4 sides and the alphabet size is 4. So there are 4 possible outcomes from which our DNA is made up of. The objective of understanding or learning this hidden Markov model is to identify the unobserved or hidden states from the sequence of symbols. So what we observe in nature is we observe symbols, and our objective is to infer how many states are there while just looking into those symbols. So states are kind of hidden. What is in front of you is sequence of symbols. Let's see, we have a sequence of symbols like this. These are some results which somebody recorded from throwing off these die multiple times, and we observe this kind of a data. So the objective of this hidden Markov model is to go back and look into which part of this sequence is coming from a fair die or which part is coming from a loaded die, and what are the probabilities which are associated with them. So we have the sequence of symbols and it is in front of us. What's hidden part is those states, and our objective of this HMM is to find something like this, where we can have, while looking into a data like this, we can classify that our system is made up of 2 states. One of them is fair, one of them is loaded. And what is the probability of staying in a fair state out of 100 trials or 100 throws of the die? 95% of the times, or 0.95 is the probability that it will stay here. A fair die will be used. And if a die is used, this fair die is used, what is the probability of each symbol? So that thing is called as emission probabilities. So you are in a state, how those symbols are emitted in this state. So that is 1/6 or equal probability if it's a fair die. Now moving from one state to another is actually the transition. So we are transitioning from one state which was fair to loaded. The probability is 5%. So that thing is transition probability. Again, from a loaded state, it can stay in the loaded state with the transition probability of 0.9. It can get back to fair state with a probability of 0.1 10% of the times. While in the loaded states, we see that half of the time we observe a 6 and rest of them are 5/6. So everybody gets a probability of 1 out of 10. So it's pretty small probabilities because this die was actually loaded. We can look into this thing one more time in this example, which is pretty simple. Here we are throwing the coin. So there are 2 possibilities, tail or head, and we observe some sequence. So that is coming through either fair or loaded coin. What is X in this case? So this X is actually the sequence of states, sequence of these symbols. So we observe the symbols and in the shape of a sequence. So that sequence we call it as X. What is pi? Pi is called path. So path is what are the underlying states. So for example, if we see the first tail that is coming from a fair die, so we see there is a sequence following beneath this sequence of symbols. There is a sequence of state which is following that. So fair, 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 and then we have biased, biased, biased. So that is we call it as path or sequence of states. Now, what is the probability while it's coming from one of these states? What is the probability within each? So that thing we call it as P of X of I while we are in pi of I. So for example, probability of having tail from a fair die over here is half, whereas coming probability of seeing a tail in a biased die is 1/4. So that is this thing right over here. So probability of xi observing a symbol in x, any symbol over here we see t at this particular position I, while the path is by I. So over here we have this biased state. So path or state sequence is the sequence of states. We call it as path, and the ith state in the path is called as by I. The overall chain can be characterized by these transitions. So we have state transition moving from state k to L. That can be taken as the probability of pi I is equal to L, while at I minus 1 state, one step behind or in the previous location, the state was k, whereas A naught k represents the initial probability starting with k. So the transition probabilities are given by a transition matrix. So that is, we have in the rows and columns, we have all those states. So it is moving from one state to another. For example, a system is in fair state, so it can stay as fair. So this is actually staying in the same state, or we can say fair to fair. This is the probability which is moving from fair to a biased state. Same way we have biased to fair and staying in bias. So that matrix is actually, we fill up with those actual numbers. Say suppose for example here it stays in fair situation as 0.9, then this is 0.1, both of them this 1. Same way we can come up with some probabilities for the bottom row. So overall this matrix is called as transition probability matrix, which is Q by Q. So on both sides we have states in the rows and in the columns. Whereas the emission probability is, now you are in one state, so what symbol you emit. So on one side you have symbols and on the other side you have states. So hidden Markov model is a statistical model in which the system being modeled is assumed to be a Markov process when unobserved or hidden states.